In today's Do Now, we're looking at a table of values with x and y, and we're going to write an equation that relates y to x. So I want to look for how are we going from x to y? What's the relationship? So as I look at this, I see if I take every one of the x's and I square it, it's going to be equal to what the y value is. 5 squared is 25, 4 squared 16, 3 squared 9, and so on. So I would say that y is equal to the x value squared. Part 2, we're asked, is this equation linear? So I would say no. The equation is not linear. There is a variable. With an exponent other than 1. We also don't see that consistent pattern in the table. As the x's increase by 1, the y's aren't increasing consistently. So that's another clue that it's not linear. We're on page 9 in our booklet today. We're going to use a word problem to discover rate of change and initial value. A tropical storm becomes a hurricane when wind speeds are at least 74 miles per hour. When Tropical Storm Helena enters the Gulf of Mexico, its wind speed is 66 miles per hour. The speed continues to increase at about 2 miles per hour. Write an equation to represent the wind speed y in miles per hour after a certain number of hours x. Okay, so we're going to write an equation, y, it's going to be y equals, to represent the wind speed after a certain number of hours x. The speed increases about 2 miles per hour. So we can represent by doing that 2x. When it starts in the Gulf of Mexico, its wind speed is 66 miles per hour. So it starts at 66 miles per hour, and then every hour it increases by 2 miles per hour. And that's really sort of the setup of the problem that makes sense, doing 66 plus 26. I'm going to suggest we use our commutative property and write it instead as y equals 2x plus 66, because that's going to follow that slope-intercept form we looked at yesterday, where we have our y, our equal sign, our x term, and then our number. Okay, so we're going to make a table of value. We're given our x values 0, 1, 2, and 3. So we have our equation y equals 2x plus 66, and we'll substitute in to find our speed y. So that's going to be y equals 2 times 0 plus 66. So that'll be 0 plus 66, or 66. So that first order pair is going to be 0, 66. We'll substitute in for 1, so that's going to be 2 plus 66, which is 68, and I'm seeing a pattern as our x's go up by 1, our y's are increasing by 2, so hopefully that pattern will continue since it's linear. That's going to be 4 plus 66, which is 70. Still going to fill out the full table, not just going to rely on the pattern. We're proving our work. We get 72, so 3 and 72. So now we will graph. So hopefully you remember from science, right, our x, our time, always goes on the x-axis on the horizontal, so that's time, and we're always going to label our axes. Our axes will always be labeled. Okay, y is going to be our speed. We can do that in miles per hour. Okay, and we have to come up with a nice scale for both of our axes. Okay, so we know we start 0 here, and then we've got some options here. We can go by ones, we can skip a line. I'm going to suggest we skip a line and go by ones for our time. 2, 3, 4, and then 5. And notice how I'm writing it in line with the line. And then our speed, we're going to have to put in a break there to show we're skipping information. Okay? And then let's see, if we do 66, 68, 70, maybe we can do 60, 62, 64, 66, 68, 70, 72, 70. Yeah, let's start at 60 there in our break and then go from there. And this is kind of all from practice, and I want to make sure, you know, my axes, I'm going to be able to see those y's, know why I was using even numbers, not odds. And now we can go and plot. So we had 0, 66, so that'll be right there. Let's see, 1, 68, 2, 70, 3, 72, and that's it. That's the information we have. And some of you might have suggested a different scale, which would have been fine. Now here we're just in quadrant 1, so when we graph, I'm going to extend through the quadrant and just put a line on the right side. Put my arrow there, right? We're going to label with our equation, and we're going to put a title, and maybe I'll call it, you know, Tropical Storm Helena. Okay. On 3, number 3, we're asked what's the initial value, right? Initial means start, right? We started at hour 0 and our first value was 66. So I would say our initial value was 66 miles per hour. What does the initial value represent? So that's the wind speed at 0 hours, or we can say when the storm enters the Gulf. Okay. And I want us to just take a second and look at where do we see the initial value? We should be seeing it a few places. One place we see the initial value is right here. We see it in our graph. It's that y value when x is 0. And these are some important notes for us to take. It's going to help build our understanding. We should also see it in our table, right? Again, we see our initial value, right? That y value when x is 0. And maybe most importantly, we see it here in our equation, right? We see it added into our equation. It's our constant there, okay? That integer, that constant, okay? You might see it here too in our generic form of our equation, our initial value. Okay. Number 5, we're asked, what is the rate of change? So what's changing in this problem? Well, the wind speed is changing. How is it changing? Every hour, our wind speed is going up by 2 miles per hour. So we're going to say our rate of change is an increase in 2 miles per hour for every 1 hour. So we're an increase of 2 miles per 1 hour. And I'm showing it like this for a specific reason we'll see later on in the week, that we're showing our sort of our increase in y's over our increase in x. Okay? What does the rate of change represent? Well, it represents the change in wind speed. Okay? And we want to also notice, where do we see that in the problem? And I think maybe the first place you see that in the problem is in the table, right? So we see our speed going up by 2, while our x's are going up by 1. It was that consistent pattern we saw as we went through. So that's our rate of change. We should also see our rate of change in our equation. where it's the coefficient of x. So here that would be that m. That's our rate of change, the coefficient of x. Many times people don't initially see the rate of change in our graph, and it actually is there, because if we think about how this line is going, it's going up 2 in our y, 68 to 70, and then up 1 in our x values. Okay. And lastly, we want to know, when does the storm become a hurricane? Okay. So our problem told us it was 74 miles per hour when it becomes a hurricane. So based on my graph and our pattern, that should be at 4 hours, right? If we continue our pattern, that would be at 4 hours. Okay. We also could have used our equation to figure that out. Right? We know the wind speed of when it becomes a hurricane, 74, and then we could have solved algebraically for x to find the hours. And we also would have gotten 4. So just another option. Today you'll be working on pages 10 and 11 for classwork. I want us to take a look at problem number 2, and it's on page 11, just because it's a little bit of a different type of problem. Allison received a Starbucks gift card in the amount of $36. On average, she spends $4 per day at Starbucks. Write an equation to represent the balance of the gift card after a certain number of days x. So we know we start our equation y. Now if we think about this problem, it's a gift card. So you start with $36 and then every day you're subtracting $4. So you would be subtracting 4x. Now, like I said, we want to keep that slope-intercept form where we have our variable term before our constant. So we'd want to write it as negative 4x plus 36. And that's a notation thing. And with that rate of change being negative, we're going to see a line that goes down through quadrant 1. Today's math jokes for Matthew folks is very timely for our unit. I'll do algebra, I'll do trig, I'll even do statistics. But graphing is where I draw the line. Have a great day.